Hi, my name is Haritaya Rajula, and I'm going to present about air pollution, advection diffusion equation for predicting diffusion and pollutants in the atmosphere for the class D generator modeling for physical process. Problem statement is to predict the rate of diffusion of the pollutant in the atmosphere based on the wind speed and current concentration of pollutant in the atmosphere. Air pollution poses a significant risk to human population and environment and infrastructure. There needs to be an effective model to predict this pollution dispersion and in the environment. Uh, the normal traditional models have a can be used to predict the rate of diffusion, but there needs to be a machine learning approach to solve this because machine learning gives promises an avenue to improve the understanding and mitigation of this air pollution in a more dynamic fashion because it is able to understand the complicated, intricate scenarios of air pollution. And there needs to be a integration of physics into the machine learning for more enhanced performance of the model. For this, therefore, I proposed a project works on advection-diffusion equation. The advection-diffusion equation has effectively four main terms. First, there's concentration of the pollutant at the position x and y at any given time t, and u and v are the velocity components in the x and y directions respectively. D is diffusion coefficient describing how the pollutant spreads. In my case, I have predicted carbon monoxide for that diffusion and rate is 16 millimeter square per second, and S represents the source or the sinks of the pollutant. I didn't have any source present, so basically I kept it constant for the demonstration. I've collected information from two data sets. First is UC Avance Machine Learning Repository. They have a air quality data set which collects as the concentration of pollutants across Italy for the year 2004 to 2005. And I've combined this data set with NOAA's global hourly wind forecast data set and from exactly 12 stations all across Italy, yeah, all across Italy, and combined these data set and made it into a tensor format for the next process, for the next step. The combined data set is similar to this, defining how the wind flows and different stations located. The stations are selected and so that it effectively understand models the whole of Italy so that they are from the different their wind can be considered from different stations and so it can be effectively understood. The first step I've implemented a sequential model with physics informed neural network. This sequential model has five parts. First is the initialization part, where initialization definition. The class has basically initialization function, which initializes the UVW wind components and the diffusion coefficient. The next in the next function, implement forward pass, so which basically transforms all the uh, applies a linear transformation followed by tan H activation function, except for the last layer, and and the last function is calculated. This last function involves computing gradients and to predict solution with respect to the spatial dimensions, using the gradients to compute the residual of the partial differential equation. Uh, then finally the boundary conditions are calculated. The boundary conditions are calculated using Newman's and Dirichlet boundary conditions to effectively address the boundaries of the model of the model's performance. And finally, the total loss is computed by summing with the summation of all the mean square error and the PDE loss and the boundary condition, and based on this, the sequential model was able to adapt and understand how the model should be trained effectively. And next, I've implemented LSTM architecture to compare it with the sequential architecture. In the LSTM architecture, it's the same as it's a simple convolutional recurrent neural network architecture designed for regression tasks. It has a fully connected layer FC1 and an LSTM layer, LSTM and a next fully connected layer, and the forward pass is implemented using the fully connected layer FC1. The data passes through the FC1 and then to the LSTM and finally through the FC2. Only the output of the last time step is considered for prediction. In the data prediction, the data is processed to match the expected input shape, that is 53,770, 1,9. This tensor is based on the input which I have generated from the data pre-processing step, and the data loader function is used to load the data set onto using the train loader to handle batches of the data. And finally, the training function, this only uses MSE loss function, the Adam optimizer, it iterates through every data loader, and the model is initialized trained on this given architecture. Then the training is done with the simple RNN, simple convolutional neural network classes now trained using the loss function, and which we implemented in the sequential model. And with this loss function, there was simple model modification. The loss function was calculated using the PDE loss method and the boundary condition, and the combined loss was given back to the model, and the training was kept similar, but the training of the model has been adjusted to handle the new loss computation. The inputs were reshaped to be batch, comma one, comma number of features to match the expected input share, and targets are squeezed to ensure the compatibility with the model's output. The custom loss function is used to calculate the loss. Finally, the custom loss function is used to calculate the loss during the training. Finally, this training process is done in the similar way. Coming to the results, the sequential model with physics-informed neural networks outperformed LSTMs without the physics-informed neural network. The sequential model was achieved stabilization and reduction in loss during the training, improved performance due to boundary condition implementation, enhanced the model's performance compared to traditional approach. When compared to the statistical based loss function such as MSE, the model showed superior performance for capturing complex dynamics of the pollutant dispersion. And the LSTM without the pins, as you can see, the loss indicated a fluctuation of loss value during the training, indicating suboptimal convergence. The loss was very high compared to the LSTM model, and the convergence didn't actually converge at the final stage. Uh, and finally, when coming to the LSTM's with pin, the stabilized model got stabilized way faster than and the physics informed neural network in sequential model. They can see the model was converged within under 20 epochs, and the loss was gradually decreasing. This model achieved stabilization and in a very less number of epochs, which is a very ideal case when considering environmental modeling. It has to be very dynamic, and the performance was enhanced due to physics informed neural networks, which has been demonstrated when compared to the LSTM without pins, and early stabilization indicates that improved learning showed. or faster convergence and indicating improved learning capabilities. Finally, this is a heat map with which the predictions were made, and it is observed that the major cities have a lot of pollution when it comes, whereas the mine and the cities which don't have much of are very inside or don't are not exposed to a lot of wind or pollutant have less pollutants dissolving. Coming to the future directions, I wanted to implement this complex model, the LSTM, which I picked. I want to explore other models which would be best suited for this, and do a more hyperparameter tuning for the model parameters, and then get a might achieve better results and get that, and also transform the data structure to better fit the model. Right now, I'm using the tensor with the shape 55770, comma 1, comma 9. These are from 18 different stations, so um, I'd like to make a change in the tensor structure to 2900, comma 18, comma 9, so that it would be ideal for the LSTM to understand the timestamps and get a more time series type of output, and incorporate more features and more environmental conditions to get the near ideal solution. These are the references. First is the data set I've referred. Second is the sense. The second is the second data set which I've collected this. The third is where I've seen the implementation of the second data set. Fourth paper is where I've gained the motivation to study this deep neural networks. Fifth is how I understood how to implement the advection-diffusion equation. So the physics-based paper. Finally, one of the theorem which was essential in understanding was. Thank you.